Thank you all. This is the 13th annual Isaac Asimov panel debate. I'm your host and moderator this evening, ʻniːl deGrasse Tyson. I'm the Frederick P. Director of the Hayden Planetarium, where I also serve as an astrophysicist with the American Museum of Natural History. Thank you all for coming this evening. For the first time, this event this evening will be live streamed on the internet. See, so you could have stayed home, you see. We waited to now to tell you that, see. Sorry about that. Isaac Asimov, the name is no stranger to any of us, certainly no stranger to anyone seated here tonight. He was a polymath, perhaps one of the last of his kind. Maybe Gardner was another one, who just was really great at a lot of things and bringing it to the public, and he was smart and ambitious. And Isaac Asimov was a native New Yorker, did much of the research for his 500-plus books that he's written, sourced from the research libraries here at the American Museum of Natural History. And when he died in the 1990s, we wanted to find a fitting tribute to him. There are a lot of ways you could possibly raise funds and commit them, but one we figured to have his name live on would be to celebrate his life and his science advocacy with this panel debate. Like I said, it's in our 13th year, and I just want to publicly thank the Isaac Asimov's family and friends who started the original fund to make this possible. If you join me in thanking them. These debates are designed not in the traditional sense of a point-counterpoint, 3-minute, 2-minute reply. That's what politicians do. We try to do it a little differently here. The panel debate is really a conversation that we will have. We have 6 physicists here, 5 physicists and an engineer, and it's as though you are eavesdropping on our conversation at the bar. And in that way, you get to sample some of the spontaneous thinking that goes on when people grapple the bleeding edge of scientific discovery. And so in that sense, it's a debate because there's typically not enough data to resolve the conflict. And that's where things get interesting. The format of tonight is I'll introduce the 6 panelists, one of whom will be sent in via Skype, and they'll each give 2 minutes opening remarks, and we just go straight into it. We'll do that for about an hour, and then we go to Q&A, represented by you in the audience. There are microphones up front. We will also be soliciting questions from the Twitterverse. That is a parallel universe to our own. It's there whether you want to believe it or not. Let me just give some brief introductions. The full profile of each panelist is in your program. Oh, by the way, I didn't tell you the topic of tonight. It started out where we would explore faster than light particles, based on the announcement at the European Center for Nuclear Research that they may have discovered just such objects. Then some later results, like a few weeks ago, came out that maybe there was a mistake in the measurements. We don't know. We said, well, let's broaden this. We have tremendous brain power coming to the stage. We will not simply talk about whether you can travel faster than light, but we will explore all ways modern physicists are testing the fundamental laws of nature. That is this evening's topic. Joining me on stage now is David Klein. He's professor of physics at UCLA with a specialty in neutrinos. David, come on out. Where'd you go? There you go, David. Thank you.
Okay.
We have, coming over Skype, we have John Guidice, if I pronounce his name correctly. He should be sliding onto our monitor. There he goes. Look, there he goes. John Guidice.
Thank you, ʻniːl.
Okay. He's a theoretical particle physicist at the Center for European Nuclear Research. And we will be chatting with him about the experiments being conducted there. Next is Sheldon Glashow. Shelley, come on out. Professor of Theoretical Physics, Boston University. Shelley.
Hi.
Oh, did I say he has a Nobel Prize in Physics? I forgot to mention that. I'm sorry. But that's not even the most impressive part of Shelley's resume. He's a graduate of the Bronx High School of Science. So. One of 7 Nobel laureates from that school. All 7 are in physics, by the way. Next, Christopher Haggerty is an engineer with the MITRE Corporation, specializing in everything GPS. GPS, this system we're all familiar with that prevents you from getting lost, is also, you might not know, a remarkable test of general relativity. Christopher, come on out. Next, we have a senior researcher at the Italian Nuclear Physics Institute, and it's a member of the OPERA collaboration at the, where are we here? At the Gran Sasso Laboratory. Please join me in a warm welcome, Laura Patrici. Laura. Nice. I keep trying to get the name right, Laura. She was on in Italy when the neutrinos arrived, so we have to get some. Did I leave someone out? Who did I leave out? Oh, there she goes. Thank you. Thank you. And last among our 5 here, and certainly not least, is Gabriela Gonzalez. She's professor of physics and astronomy at Louisiana State University, which is the academic home of one of the most advanced observatories of gravitational waves ever conceived. Let's give a warm welcome to Gabriela. Gabriela. So, let's get my stuff together here. So I'd like to, if we can, I'd like to know a little bit more about each one of you. So why don't we start at the far end? David, just tell us what drives you in the day. Spend a couple of minutes doing that, and then we'll get into our beer talk.
My microphone's on? Okay.
Yeah.
So I study neutrino physics. Actually, there was a picture up here of the detector I used, but it's gone now. And neutrinos were thought at one point never to be detectable. They were invented in 1933 by Wolfgang Pauli. They were discovered in 1957 by Professor Reines. So I've devoted much of my life into studying high-energy neutrinos, low-energy neutrinos. In particular, tonight I'll be talking a little later about looking for neutrinos faster than the speed of light with a counter detector to OPERA. But anyway, neutrinos fascinate me, and I hope they will fascinate you. Thank you.
Thank you. There. John Giudice, welcome to New York. At least your avatar is here in New York. If you can tell us just how you plug into the world of physics.
Sure. I apologize for my last-minute problem and not for being able to be physically there, but I'm very glad to be at least virtually there. After all, I am a theoretical physicist, so I don't care too much about actual reality. Also, it's an interesting experience because it's the first time in my life that I wear a jacket, tie, together with pajama pants and slippers. I'm a theoretical particle physicist.
So you're in your underwear now, is what you're telling us.
No, pajama pants, I said. I'm very glad that theoretical physics exists and is supported by society, because I'm not a very practical person, and probably there's not much else I could have done in life. Okay. I was educated in Italy, then I had the privilege to do research in your country. I worked at Fermilab near Chicago and at the University of Texas at Austin. And these were fundamental years for my research because they really shaped my vision of particle physics. And then finally I moved to the European laboratory of CERN, And how can I describe CERN? I think that if God were a particle physicist and if he had to create heaven, then he would build something very similar to CERN. So, very privileged to work in such an intellectually stimulating environment.
Okay, excellent. Well, thank you. Thank you for those opening remarks. Shelley, what do you got? It's your third time, I think, on the stage here.
Third time here, yes.
Yes.
Look, I agree with the previous speakers, and neutrinos are my favorite particles, too. But we're here, I think, to talk a little bit about relativity as well. And we all know that the special theory of relativity was introduced back in 1905, and there have been doubters ever since. And one of the great fascinations that I've enjoyed is looking at tests of the special theory of relativity. And let me just recall that 15 years ago or so, in the late 1990s, my dear departed friend Sidney Coleman and I got into the game as theoretical physicists to see what we could say about tests of the special theory. There had already been all sorts of experimental tests. There was an atomic physics experiment that was sensitive to 21 or 22 decimal places, done by some experimenters at the University of Washington, as I recall. Could we, as theorists, do better? It seemed an absurd question, but we did, because we realized that if, for example, particles traveled faster than the speed of light, then there would be consequences. Processes that would ordinarily be forbidden become allowed, and processes that are ordinarily allowed can become forbidden. And on that basis, we were very proud of ourselves. We did an experiment. We said, people have seen protons, cosmic ray protons of such large energies that they couldn't have had these energies if relativity were violated. And we put a limit on the possible superluminality of protons of 10 to the minus 23. I mean, that's an absurdly small number. And yes, even theorists can do experiments.
Okay.
Thank you.
And that's not even what you got the Nobel Prize for.
Well, no.
Yeah.
To be honest, that had to do with something I did as a mere infant back in 1961, a long time ago, when one of my first papers written after I graduated, got my PhD from Harvard University. By the way, I also taught there for 35 years. Gave up because 35 years is enough to teach at any place. So I got my PhD and then ran off to Copenhagen. That's a story in itself, but we'll skip that for the while.
Okay.
And that's where I wrote the paper that won the Nobel Prize.
Excellent. Christopher, what does it mean? This is your opening remarks, but you're not from an academic setting. You're in a sort of a MITRE corporation. If in your comments, opening remarks, you just tell us what that is, because I think many of us might be unfamiliar.
Yeah, MITRE Corporation is a private company that manages 5 federally funded research and development centers. I am an electrical engineer. I am live here in New York because I like things that are real. I absolutely hated my modern physics class in college and never wanted anything to do with that voodoo stuff. Although I'll have to say, I've been working for the past 20 years on GPS, and I've grown to like modern physics a lot more because it is used. Both general and special relativity are very important to the operation of GPS today, and you can see it with your own eyes. If you don't apply the corrections that Einstein derived for us, it doesn't work anymore, and I like that much better than seeing cubes from the side or whatever my textbook talked about. So that's why I'm here.
Okay, thank you. Laura.
Well, first of all, I would like to say that I'm very happy to be here and honored for being here. Thank you so much for inviting me. I'm from Italy, as you can easily guess from my accent. And I started my career, professional career, as a physicist in the so-called astroparticle physics, which is a quite new field. It dates back to the 1985, something like this. And it's a field in connection between particle physics and astrophysics, because there is a strong connection, and neutrinos are a link between those two. But anyhow, I didn't start with the neutrinos. Actually, I started with magnetic monopoles. With an experiment at Gran Sasso. You will hear about Gran Sasso later on a lot, I think, which was looking for those magnetic monopoles in cosmic rays, which the existence of magnetic monopoles would prove the unification of three fundamental forces. And then I switched to neutrinos, and okay, I am the guilty person tonight, because I am a member of the Opera collaboration, which claimed that neutrino can fly faster than light. But okay, you will hear more about this later on.
Yes, we will, for sure. Okay. Yes, Gabby.
I'm Gabriela Gonzalez, and I live in Louisiana, but you'll hear an accent from much farther south. I was born in Argentina, came to do my PhD in the US, in Syracuse, New York, and loved what I did and stayed there. I started working, even at the time, in the early 90s, on a beautiful project called the LIGO project, which is testing a prediction, what I think it's the most striking prediction of Einstein's theory of relativity, that says that space-time itself can vibrate, can produce gravitational waves. We all produce gravitational waves that travel. We are out to measure these tiny waves that come from black holes. And I've been working on that ever since. I'm the spokesperson for a big collaboration of hundreds of scientists that are working on this, and I hope I'll tell you more about that later on.
You certainly will. So thank you all for your opening remarks. I want to spend a couple of minutes before we put on the boxing gloves. I'd like to just, I want to explore just the way physics gets done today. We have a couple of you who were part of the CERN collaboration. So CERN is how you pronounce the word, which I think in French, that's the sequence of words, but in English, it's the European Center for Nuclear Research. You swap some letters back and forth and you get CERN. And that's where you have the Large Hadron Collider. And so, David, just so I go back to you, this is, can you tell me just something about this Large Hadron Collider relative to previous colliders? Just what is it and what is it doing for us?
Okay,
No, it's not. We got the mic there? Let's see.
It's drooping a little bit.
Is it going? Try again.
Can you hear me now?
All right, take that.
Okay.
I can't interrupt you. See?
Okay, good. I can speak for a long time. I worked at CERN for a long time, and we tried here in America to develop our own
You're on now.
very large machine called the superconducting supercollider, which was going to be in Texas. A series of very unfortunate events led this machine to be canceled. So CERN, which was then directed by my colleague...
Wait, just to clarify, you're describing a particle accelerator that was proposed in the United States that got canceled. And so stranding an entire generation of particle physicists here in America.
Now we understand that that may have been a tragic mistake, because at the Large Hadron Collider, which is 27 kilometers in circumference, we are hoping to see some particles which are called supersymmetric. You may have heard of those before. They seem to be at this moment outside the range of the energy. Now we do think we've seen the Higgs boson. Maybe we can say more about that later. But the energy range of the SSC might have been ideal, but now many scientists in the world, even people from Iran, Vietnam, it's just an incredible array of scientists who work on this Large Hadron Collider. I in particular work on the compact muon solenoid. There's 6 professors at UCLA that I work with, and we have our own duties for the hardware. So basically, the Large Hadron Collider has now become the world machine, but we're still hoping in the future we're going to be able to build something comparable to that in the United States. So for the time being, we're hoping there'll be major discoveries there, but the only one on the horizon at this moment is the Higgs boson.
John, at CERN, how many different countries are involved there? just to get a sense of this.
Right. So the member states are about 20, but in the LHC experiments, a lot more countries are represented. Essentially, I would say almost all countries in the world, of all continents. I mean, hundreds of countries. It is really a truly international endeavor. And that's a nice thing. You know, when I was saying that CERN is heaven, there's much more than physics involved. It is really the idea that science brings people together, joins nation. CERN was born, was funded soon after the war. And as you can imagine...
But this is America, so you have to be specific about which war you're talking about. Funded after the war. Please specify.
It's the only one that is in my view as an Italian.
Second World War.
That's the Second World War, and as you can imagine, Europe was divided and also was destroyed, did not have the resources to fund fundamental research. So at that point was a special political endeavor to bring together nations that were just fighting a few years earlier. And science was this vehicle to bring people together and also to start something new, to bring back from the United States many of the scientists that had to leave and starting in the ashes of destroyed Europe something new. And I think that mission was really a success. And now we see that CERN is expanding even beyond the borders of Europe, and it's truly the biggest and most international center for science at the moment.
Excellent. So it'd be fair to say then that CERN in Switzerland and the International Space Station are two examples of extraordinary international collaborations, perhaps the greatest international collaborations outside of the waging of war. Would you agree?
Yes.
Yeah, okay.
That's good. I wasn't sure you were referring to me because you're looking at David, at least from my point of view, but that's what I said, so I certainly agree with what I said.
All right, I want to spend a little time just starting off thinking about what it is to test what we call fundamental physics. And Shelley, let me ask you, are people still testing thermodynamics or sort of Maxwell's equations, these classic physics from the 19th century? Or is that just in the books and we're on to other things? And if we are on to other things, why ignore 19th century physics and only test 20th century physics?
Well, yes. Let's pick...
My question was not a yes-no answer. Just so you know, I'm onto you here. Go on.
You mentioned many things. Let's think of classical mechanics. Think of the mechanics that was... You know, that apple fell on the head of Newton and he created classical mechanics, F equals ma and all that stuff. That's a great theory. It is true. It is a true theory. Now, what the hell could I mean by that? Because it's not true for things that move too fast. When things move too fast, you have to invoke the special theory of relativity. It's not true for things that are too small because you have to invoke quantum mechanics. It's not true for things that are too big and fat, like the sun, because general relativity begins to play a role. So why do I say classical mechanics has proven to be true? Because we have mapped out its envelope of validity. We know exactly where it applies and where it doesn't apply. And I think this is, in a sense, the modern definition of truth in physics. We have quantum mechanics. We know, to a certain extent, its boundaries. We know Maxwell's equations. We know that it falls apart under certain circumstances where light behaves as particles. We know the boundaries of
Okay, that's an important distinction.
Theories.
So when you conduct experiments to test these theories, you're not testing them within the realm where you're pretty sure it falls within the boundaries. You're designing tests at the boundaries.
At and beyond.
At and beyond.
Exactly.
At and beyond the boundaries. Gabby, you are at and beyond the boundary of Einstein's general theory of relativity. A reminder And correct me if I'm wrong, allow me to make this generalization that special relativity of Einstein, 1905, was his extension of Newtonian mechanics, motion, essentially, and then general relativity was Einstein's extension of Newtonian gravity. Is that a fair way to think about it?
Exactly.
Yeah, okay, good, good. That was a very grumpy yes, but I'll take it, okay. But yeah, all right, you've got to say that. All right. So Einstein is looking pretty good every time I've ever looked at it, yet somehow you have some doubt, apparently because you're involved in a very expensive experiment to test it. So let me ask you, are you testing it because you think he could be wrong, or are you testing it because you're trying to show him to be right?
I'm very convinced that Einstein was right.
Okay.
We are testing it because we are measuring this prediction that has never been measured before. Einstein's theory in one of the most straightforward predictions is that masses, they attract each other not because there is a force, like Newton said, but because they distort space-time and then they fall into each other's space warps. And it is those space-time ripples that we are trying to measure, which are very, very tiny, and that's why they haven't been measured before.
Okay, so what's an example of what will ripple space-time on a level that you'll be able to measure?
We are measuring...
Wait. We're all rippling space-time here, aren't we?
We are, yes.
Okay.
We are all waving
Okay,
space-time
but you're not
around
measuring that.
because it's too tiny to measure. And that was Einstein's prediction. Einstein said that these things would never be measured because
Okay.
they were too
Well,
small.
what did Einstein know? Gosh. Okay.
What did he know? He didn't know what technology we could have.
All right, so
We used his theory to calculate how big this was. And what his theory says is that these gravitational waves are coming to Earth maybe once every year or so, changing the distance between the Earth and the Sun by an atomic diameter.
whoa, wait. Okay. Okay, so wait, back up. So these ripples you're trying to measure is like
tiny.
a wave through the fabric of space and time. And when you have a wave, it sort of distorts, it's like the fabric shrinking or expanding,
That's right.
I guess. Okay.
Exactly.
So in the 93 million mile, this is America, so it's miles, sorry. Okay, 150,000 a million kilometers, yes, okay.
A parsec.
So that distance from Earth to the Sun changes by the diameter of an atom from that wave, and you're going to measure that.
We are actually going to measure on a much, much smaller scale,
Okay.
which is still very big. It's 2.5 mile scale. So we have these huge observatories.
2.5 miles is much smaller than 93 million miles.
It is a lot smaller.
So you're looking for
and
a
it's still
shift-
very expensive. But
You're looking for shifts much smaller than the diameter of an atom.
that's right. We are looking for shifts that are smaller than a proton, a part in 10,000 of a proton diameter.
Okay, then you woke up, and then you said, okay,
The most exciting thing is that we have measured already a part in 1,000.
I mean,
Of a proton
if a
diameter.
wave came at a part in 1,000, you would have seen it.
Yes.
But
and
none-
it didn't come yet.
Okay, but that hasn't happened.
It hasn't happened
And
yet.
you're after a part in
10,000.
10,000. Okay, factor of 10. Okay, we'll get back to you on that. Okay. Miter dude.
Yes.
Chris,
ʻniːl dude.
you know, someone should tally how many people are not dead because they didn't have to read a map while driving the car. An unfolded map across the
And
windshield because they were guided by GPS.
You'll have to offset that from those that are dead from looking at the GPS or programming their GPS.
So it's all balances.
Yes.
You're a big GPS guy. We all love, who doesn't love GPS? Of course, it started as a military project, and I'm guessing the military wasn't thinking, what a great test for Einstein relativity. They probably weren't thinking this, isn't that correct?
Probably not, but they knew a lot more than we think, going back through some of the old papers that were written even right around 1970 or so. They knew a whole lot of things that we rediscover now and then.
Well, it seems to me they're going at like orbital speed, right? That's fast, but it's not speed of light speed, right? It's
yeah,
a couple of tens of thousands of miles an hour, right?
The satellites are going about 4,000 meters a second, which is a little over 8,000 miles an hour.
8,000 miles an hour?
Yes.
So that's pretty high up then, okay.
About a New York taxi driver speed at a yellow light.
New York taxi driver speed at a yellow light. This was the analogy. That's a new unit of speed.
Yes.
All right. And so, but that, you know, I remember my relativity equations, and you have to get pretty close to the speed of light for it to really matter. And so I don't think of GPS as being any kind of test of relativity at all. So how does this surface as a benchmark for it?
Well, what's interesting is you're mentioning the effects of special relativity that says if you have a clock up in space, it's whizzing around, you'll actually see it from the ground as running too slow. But the effects of general relativity are actually bigger for GPS. The fact that it is 20,000 kilometers above the surface of the Earth makes that clock appear to actually run fast. And the clocks that are put on the satellites are actually intentionally set slow by about 5 parts in 10 to the 10th, so that they'll appear to run correctly as seen here on Earth. And that's something that's done in GPS.
Whoa, you just blew my mind. Wait. Did you just say that the clocks on the GPS are intentionally designed to run at a general relativistically slower rate, just so that when we observe them from Earth in a deeper gravitational setting, they will look accurate to us?
Not just general, it's actually the combined effects of general and special, but general relativity has about 6 times greater effect than special relativity. Special would make them appear to run slow, general would make them appear to run fast, and general's bigger, and the net effect needs to be compensated within the system. And not only that...
Okay, just to remind people, okay, yeah. That's enough. My mind is blown. I'm done. Good night, everyone.
Let's go for an explosion here then. But the interesting part is the satellites aren't perfectly in a circular orbit, so that there are imperfections there where they are slowly going up higher sometimes and going lower sometimes, which means the speed isn't constant and the gravitational effects aren't constant, and the user equipment actually compensates for that, taking the ellipticity, the non-circular nature of the orbit into account in every piece of equipment that's out there, including probably the stuff in your phone.
So it's one thing to be high, low, and in a lesser part of Earth's gravitational field. Mm-hmm. All right, so now that means they'll run a little, get this right, faster, because as you're deeper in a gravitational well, your time slows down from general relativity.
Yeah,
okay. So now these orbits are not in perfect circles. Mm-hmm. When you're not in a perfect circle, sometimes you're close, sometimes you're far, and that difference is measured.
That difference is compensated in virtually every GPS receiver that's out there. If you didn't, you wouldn't get the several meters accuracy you'd get about 10, 20 meters accuracy.
So that's because what you're saying is, not to put words in your mouth, but just so I understand it, that the time precision translates into location precision on Earth.
Correct. Yeah, the GPS is an arranging system. It's measuring the transit time of signals from the satellite down to the user on the ground.
All right, so if you did not correct for general relativity, and I'm here, where's the satellite going to tell me I'm standing?
If you let the clock run on the satellite for 1 day without compensating it, the clock would be in error by 38 microseconds or so, which would be about 11-kilometer ranging error after...
11 kilometers?
Of one range measurement, and your position would be off by something commensurate with that.
Yeah. I can't even continue.
Hey, ๊niːl, can I translate the previous discussion into English?
Okay, go ahead. Go ahead. So now we can find another way to blow my mind. Okay, go ahead, Shelley.
No,
yes.
Not at all. If we did not have Einstein's general theory of relativity, well, it could have been somebody else's general theory of relativity, but if we didn't have the theory of general relativity, we would not have GPS. It's as simple as that.
Okay, I mean, this is, all right, so can
I add one thing?
Yes, please. Yes.
To this, then if one wonders what's the use, again, of studying things so academic like relativity, like Einstein was doing, what's the use of that, the practical use of this? Then you may discover later on, very long time after. So the
In
point
1916, surely no one was saying, this is some practical stuff, Albert.
Yeah.
Right, that's probably
Yeah.
was not what he was hearing in the
yeah,
coffee lounge.
Yeah, in fact.
My favorite equation of Einstein's, just while we're on the subject, is when he derived the stimulated emission of radiation, his famous Einstein A and B coefficients is what they're called. We study that in astrophysics, and that's the equation that enables the construction of lasers. And so Einstein, at the time he wrote that, was not saying, barcodes, yes, this is how I will, this is where this will land. You know, I'm thinking, but it's an appeal for basic research is what you have here. So can you flip this question around and ask, rather than pre-compensate the satellites for general relativity, can we use GPS to test the limits of relativity? Or are you so within the zone that Shelley just described that you're not going to land, you're not good for that?
Yeah, in some ways, you can use it to measure relativity. In fact, before the first GPS satellite was launched, there were a series of experimental satellites, navigation technology satellites, they were called NTS-1 and NTS-2. And the engineers at the time weren't all believers in that relativistic corrections would need to be applied. So they actually had a switch on the satellite where they could turn it on or off. But they actually ran it with the clock running at the right rate, factory set on ground, and they ran it and measured the offset, and it was consistent with what you'd predict using special and general relativity, and that sold the engineers anyhow.
So the engineers didn't believe Einstein?
Not all of them. In fact, I believed Einstein until tonight, until we went up into your reading room upstairs, and I saw Einstein in a light I had never seen him before. What is Einstein wearing in your office up there?
Oh, in our research library up in astrophysics, there's a bust of Einstein, and he's wearing a New York Yankees
So I don't
hat.
know about him. He's from Boston too, but I'm a Red Sox fan, so I don't know. I'm starting to doubt this all.
Red Sox fan, wrong place to say that, let me tell you.
We do get to leave through a different exit, don't we?
I'm just saying. Where's all my stuff here? So I'm impressed by this, and so this continues. So it was a few months ago, we learned of how many months ago, that there's the possibility? 6 months ago, thank you. How'd you know where I was coming here? So, 6 months ago, we learned of the possibility. No, it was longer ago, where we learned that maybe the neutrino, one of the fundamental particles of nature, may have been misbehaving. That is not following what we'd expect it to do. In particular, there was a claim that it was traveling faster than light. John, could you just update us on the original papers that led to that?
Yes, so on the 23rd of September, there was this big announcement from the Opera collaboration.
And Opera is an acronym, and please tell me what each of those letters stand for.
I think Laura can tell you.
Oh, okay.
He doesn't know.
Yes, actually, we're going to get back to her, so I'll save it for her. Please continue.
Okay. All right. I know what opera means in Italian, and I think most of people know, but actually don't know what the acronym means. Mm-hmm. So on the 23rd of September, there was this result, and of course, at that point, many theoretical physicists were startled as soon as they heard about this result, and immediately they tried to make sense of it. So for several months, many physicists worked very hard to understand if it is possible to modify the properties of neutrinos or the properties of space-time to reconcile the opera result with our knowledge of special relativity. Because the opera measurement told that neutrinos, as they travel from CERN to Gran Sasso in central Italy, they arrive with 60 nanoseconds of advance with respect to light.
60 nanoseconds?
60 nanoseconds, maybe it may seem not a lot, but
It's 60 billionths of a second. 60.
That's right, but that's a lot. For a particle physicist, that's an enormous quantity. So that's why people really jumped on that chair And
And
immediately,
just to clarify, you send these particles from Switzerland through the Earth, in a
That's
cord through the spherical Earth, landing in her lab.
That's right, 732 kilometers. And we take advantage of the curvature of the Earth because the neutrinos are very elusive particles. They see the Earth as a perfectly transparent medium, so they can cross the Earth with no problem. Although, as you may know, the Italian Minister of Science claimed that Italy had built a tunnel going from CERN to Gran Sasso in order to allow neutrinos to go through. That was the Italian contribution
John,
to the
it's
project.
not fair to say.
We're coming to you
Never
in
say
like
anything
3
bad
minutes.
about
Okay.
politicians. Sorry about that.
Yes. So 60 nanoseconds, if we do that in sort of English units, the light moves 1 foot per nanosecond. So the light got there 60 feet ahead of when the neutrino got there, would have beaten a beam of light by 60 feet. I think that's
Right. That looks a lot longer, and indeed it's something that in units of particle physics, this is an enormous effect. Much big, billions of times bigger than anybody could have guessed from the fact that maybe relativity, when it enters the quantum regime, should be modified. So immediately many of us try to make sense of this result and see what was the meaning, because that's part of our job as theorists. But at the end, I would say after a few months, there was a general consensus that this reconciliation seemed really nearly impossible. I would say that there was only one plausible theoretical explanation that I heard about this result. And as you know, the neutrinos travel from CERN in Switzerland to the Gran Sasso laboratory in central Italy. And the explanation goes as follows. When the neutrinos are produced in Switzerland, they travel at the speed of light. But then, as soon as they pass the border and enter Italy, they no longer respect rules and speed limits.
okay.
That to tell you what really was the status of theory. At that point, really the general consensus among theorists about this inexplicability of the opera result. And this came earlier than the statement of the 22nd of February by opera announcing the experimental problems. So I think that this story has a good moral for theoretical physics. Because yes, we are eager to chew on every bone that experimentalists throw at us, but we don't swallow anything.
Especially not the chicken bones. You don't want to smell it. So, Laura, so he sends the signal from CERN. You receive the signal in Italy. And now these are misbehaved neutrinos. So either Einstein is wrong, they did something...
It's not correct to say misbehavior.
Misbehavior.
I mean, if it...
Surprising behavior.
Okay.
Okay. So either Einstein is wrong,
Yeah.
they messed up on their end, or you messed up on your end. Or all of the above. So where do you...
John already anticipated that the result has to be corrected, that we found faults in our equipment. It was quite a surprise because we had retested many times all the different parts. It is a quite complicated experiment that of measuring the neutrino velocity. So it had been checked, but eventually we discovered that there was something very, let's say, stupid, that apparently was not put in the proper way. It was a so-called faulty connection. It's not so simple as this, somewhat more complicated, but we can summarize like this, a faulty connection, but it's not so simple as this. And well, I cannot say which is we found two different effects. One which goes into the direction of making neutrino slower than they appeared at the first time, and another effect which makes their velocity to increase. So the combination of these two effects very likely will cancel the anticipation that had been measured. And so, in any case, but can I comment concerning all the interest? I mean, John, concerning all that you theorists have been doing, there was a lot of steering, even though now very likely we know that the result is not what seemed. It stirred a lot of interest, a lot of discussion, a lot of reconsideration of so-called facts. And this is perhaps the gift, the unwanted gift that at the end, eventually, opera has done to the community.
And tell me what the opera stands for?
Oscillation project with tracking apparatus. And then you have to ask me why.
Why?
Because the main aim of this experiment was not to measure, is not to measure the neutrino velocity. It is to prove, to give the final proof of an effect that a neutrino can undergo, that is the so-called neutrino oscillation. Neutrino, which exists in three families, which we call neutrino, electron neutrino, muon neutrino, and tau neutrino, as they travel, they can change their nature from electron neutrino to, for example, muon neutrino. It's a peculiar property of those particles which prove that they have mass, they have a mass. Neutrinos were thought before to be massless. Anyhow, this was discovered in 1998, but it was discovered somehow in an indirect way, and opera was aimed at proving in a direct way by a so-called appearance experiment that this is what really happens. But then you have to give me some more time if you want that I explain it better.
Okay. Well, I'll come back to that. Let me just come over to, where are we here? David, I've got a research paper, pub date 15th of March, 2012. That's 5 days ago. Measurement of the neutrino velocity with the Icarus detector at the CNGS beam. Okay, so you're a co-author on this paper. What does it say?
Okay, let me say two things first. Let me go back to Shelley's comment and say one thing about relativity. Every time a machine like the Large Hadron Collider works, it tests relativity. Now, these, in some way.
Wait, just a quick second. Is this a picture of LIGO here?
Yes.
Yes, in Louisiana.
That is LIGO. Right. LIGO Livingston. LIGO Louisiana.
Louisiana. And it has three.
Oh, no, this is the road.
Oh, that's the road? Okay.
We have to get there.
Okay. That's the road, and then we have two beams at right angles.
That's right.
Okay, and how long are those?
2.5 miles.
Each?
Each.
Okay, good. Just since we have the photo. Sorry to interrupt. Continue.
Okay, so let me just say, more or less finish up what Shelley said. We have tested these fundamental principles, like Newton's law of gravity, all the way from millimeters to thousands of, or even millions of light years. We don't make these things sit quietly. In other words, when something has been tested that well, we start believing it's real. Now, in terms of the neutrino, faster than light, already there was a measurement of this when the supernova 1987A went off, and neutrinos traveled 150,000 light years to the Earth and arrived here within 20 seconds. That resulted in a limit on the neutrino, this time electron neutrino, velocity being less than about 1 part in 10 to the 9th the velocity of light. Now, in this Icarus experiment, which you had pictures up here before, it's a very large vat of liquid argon, about 600 tons. It's absolutely non-trivial device. We believe it will be now followed by a huge detector in South Dakota that will actually be 40,000 tons. This is one of the futures of science in our country.
But just a quick second, just to clarify, you mentioned supernova 1987A.
Right.
This is a supernova, the first supernova observed in the year 1987, and it was observed to go off in a nearby galaxy to our own, a dwarf
Large
galaxy.
Magellan Cloud.
Yeah, and it's visible from the southern hemisphere.
Right.
And we can see the exploding star, so that's when the light gets to us. And then we had a detector that measured the arrival of neutrinos.
Two detectors.
Two detectors, and they came in behind the light, not ahead of it.
Right. About 20 seconds of time the pulses lasted.
Okay, so
even though it traveled 150,000 years to get here. So it showed conclusively that the velocity of light was extremely close, the velocity of the neutrinos were extremely close to the velocity of light. Now, in
Those neutrinos.
let me finish now. I'm going to get to the other neutrinos now.
Those were
okay?
not
So,
detected.
Those weren't CERN neutrinos.
That's right.
Those were supernova neutrinos. Duh.
I don't buy the argument that neutrinos change when they go into Italy. So what we have done is in this big liquid argon detector, which is, I think, going to be a marvel of technology in this country someday, we have looked for neutrinos coming from CERN, 731 kilometers, and this paper that we were just talking about a moment ago, which we're publishing, shows that the neutrinos arrived exactly with the speed of light. And the second experiment, which we did earlier, using Shelley, one of Shelley's theories, we follow him very closely.
Isn't it great just to have theories people just select from and, you know.
No,
they apply?
we know his theories are right, so we usually. Anyway, one of his theory contributions, which has been very important, if there were such high energy neutrinos with faster than light particles, they would emit a large number of electron-positron pairs, positron being an anti-electron. In the same 600-ton liquid argon detector in the Gran Sasso, we've observed no pairs. Now, there was a plot up here before, which has been taken down now, but which showed our conclusions, which were very similar to the supernova 1987A. So we have shown in two ways that the neutrinos, mu neutrinos, have exactly the speed of light or possibly slightly less because of the mass. And we entirely disagree with opera.
Okay.
Can I comment?
I
So
can add.
he disagrees with you, Laura. But let me ask, before I come back to you, David, you just cited two different neutrino experiments. So the fact that you're now saying they're wrong has to assert that all neutrinos behave the same way in all situations.
Yes, we don't have any
I'm
evidence.
echoing Shelley's point here.
We basically have seen now thousands or even millions of neutrino interactions in different venues and different process, different countries, different continents, and we've seen they all behave the same in their interactions.
Okay, so
So
Laura,
why would they change now? Because they're coming from CERN through Italy.
So Laura, so if I understand we spoke earlier that there's still a collaboration and a published paper being prepared, so and you can't really talk about that, but what does your gut tell you about these neutrinos that were measured by OPERA?
David already told us.
He already knows the answer.
Yeah. So, at least but...
What you really meant by that is he thinks he knows the answer. That's really, I think, what you meant.
What I mean is that we found those problems that I was mentioning. And when you put all them together, likely the result will be in agreement with what Icarus found. I want to point out one thing concerning Icarus. Icarus is, as David said, it's another experiment located in Gran Sasso. But what they measured is not completely independent. It's not exactly another experiment. It's another experiment only for the last part of the experiment itself. They took OPERA's data, OPERA measurements concerning the baseline, concerning the synchronization of the timing, the same that OPERA had established, that had set. And then they simply used their timestamp for their event. So down to Gran Sasso, from CERN down to Gran Sasso, the elements of the computation are exactly those that OPERA had set. And then they were able to provide a more accurate measurement of the last part. So if there is anything wrong in the upper part of the experiment, they have the same error. Am I correct?
I don't agree. We can talk about it later.
No, talk about it now. What do you mean talk about it later?
We have the right answer. That's the key thing. And we have certified it. We measured it actually twice.
What?
Assuming Professor Glashow's theory is correct, of course. If his theory is...
It's not a theory, it's physics.
Okay. Therefore, it must be right. Okay. It must be right. Therefore, we have checked ourselves, so to speak. So I think we would be willing to probably make a wager, although scientists are not supposed to bet on things like this.
You can bet a bottle of Italian wine. Go on, go on.
Bottle of Chianti.
No, Barolo, not Chianti.
Okay.
Fine.
I will bet that
Montepulciano.
Icarus is correct and opera is wrong. It will pay off. I'll come to Bologna.
Again, as you know better than me what a systematic error is. So you have the same systematic error as we have down from CERN down to Gran Sasso, because you used exactly the same data. The baseline was what we had measured. The
And why do we get different
synchronization-
results?
Oh, this is physics. You have to test even this, no? Isn't it?
Okay, well,
So, if I understand correctly, the timings that were invoked here to assert that we had these neutrinos behaving differently were measured by GPS satellites.
Yeah.
Is that correct?
Yeah.
So it's his fault.
No. In fact, when we got this anomaly, for sure, it didn't represent any I mean, it was not that Einstein was wrong, exactly because we were using Einstein or anyhow relativity to do the experiment itself. If it was true, if the result was true, it simply means that you had to, as John Giudice said, to invent a way to reconcile, to put all things together. It was not that you were disproving Einstein. Also, in the newspaper, it was put like this.
Yes, that was
opera was disproving. It's not like that, and we didn't say like that. We didn't say
make a
this.
comment?
That's the press.
Neil, can I say something?
Yeah, John, yes.
Because now it looks like maybe to people that this was just the point was measuring some properties of neutrinos. And I think at stake here there was much more. That's why theoretical physicists were so interested, because Einstein revolutions was showing that space and time are two conceptually identical aspects of a single physical entity, which is space-time. And the zipper that keeps together space and time is a principle of an absolute velocity, the speed of light, or the speed of any massless particle. So if neutrinos were faster than light, neutrinos would see space and time differently. So opera, in a sense, would have unzipped space-time, would have broken the symmetry that links space and time. So not only special relativity would be in danger, but our vision of space-time. In other words, the entire stage on which we build our theories.
Why
so
wouldn't
at stake here, there was much more than just measuring the property of a neutrino.
Would it be in danger only at the limits of relativity, or would it be a problem fundamental to the corral that relativity had established?
See, the problem is that we believe that there is, as Shally was saying, every theory has a range of validity. So also relativity will have a range of validity at the stage in which it reaches the quantum world, because quantum mechanics and the general relativity, the way they are not compatible in the way we know them. So we expect that at a certain level, that symmetry between space and time may be broken. The problem is that the fact claimed by opera was so huge that it was putting at a level which was well within the range in which we have tested special relativity. And that was a shock. And that's why it was so difficult to reconcile the claim made by opera with our previous knowledge and test of special relativity.
You should know that because of that result, I got like thousands of tweets at me saying, "What do you think of this? What do you think of this? Is it the end of physics?" And I said, given how long relativity's been tested and our understanding of particle physics, it's probably wrong. That's like the first most likely explanation. Second, Shelley, haven't we physicists spoken of faster than light particles before? What's so violating about that? Tachyons, for example, are faster than light particles, hypothetical. But they're consistent with relativity. Nobody complained about them.
Yes, it's hard to complain about particles that don't exist. But let me say a word about Bronx Science at this point, because one of my buddies at Bronx Science was Gary Feinberg, and he coined the word tachyon.
Is that right?
Yes.
Excellent invention. I must. Tachyon from the Greek root tachyon, meaning fast.
Like
yeah.
tachycardia. Your heart beats too fast. Well, I want to attack that man.
Or tachometer. You want to? Sorry. Here you go. Yeah. All right.
Can I just very
Yeah,
briefly?
Shelley. John, Shelley wants at you here. Okay, go, Shelley.
Very briefly.
I'm very glad that I'm not there, so he cannot physically attack.
Okay, Shelley, what do you got?
Well, I was going to say, give me the microphone. I didn't realize I had one here. No, look, that man, John, is being far too modest because he made a very important point very immediately after the quote-unquote discovery of superluminal neutrinos. He pointed out that as he said, this was a very large effect compared to what was already known, that it would spread. There would be metastases of violations of relativity all over the place. And I believe you wrote a paper that argued that you could not confine the violation of relativity to neutrinos. It would spread all over the place.
You have neutrinos cavorting with protons, and
and we know 10 decimal places, 15 decimal places, 20 decimal places, 25 decimal places, and now someone is saying there's a violation at the 5th decimal place? Not possible. And I think that was a very important observation.
You know what I think was the best statement ever for knowing that the measurement was wrong? I heard this. I didn't come up with this. It was because the neutrinos arrive in Italy before the speed of light. So the argument was it can't be true because nothing ever arrives early in Italy. That was the. I heard that. Did you hear that, Laura?
That's a convincing argument.
They were the ones who were sent yesterday.
You said what, Laura?
I don't like it.
You don't like that one. I want to shift topic just a little bit and go back to John. John, we spoke of relativity. There's something else out there, the standard model of particle physics. It's this organization of particles and forces. And do you feel like you're testing the standard model? Or is that another sort of zone where we're trying to find the corral where everything that works fits in the corral and you're testing the edges?
Yes, that is certainly the primary goal of the LHC, right? We have this beautiful theory, which is the standard model, but we want to go beyond. I mean, theoretical physicists are a very curious, inquisitive, and ambitious animal species. So they are not satisfied just by opening the toy of nature, inspecting the clockwork, and identifying all the springs and gears. They always want to go one level deeper, and they want to understand the inner workings. They want to understand why the mechanism works. So the standard model gives an excellent description of the particle world, and there's nothing wrong with it. So most of the questions that we are addressing today in theoretical physics are not about the consistency of the standard model, but about the reasons why the standard model is the way it is. So superficially it may seem that many of these questions are about the beauty of a theory rather than the basic structural problems. But history of science has shown that following principles of beauty sometimes can bring you very far. Remember that general relativity was not invented to explain some observed inconsistency of Newtonian gravity. The calculation of the mercury perihelion came later. In that case, the problem was understanding force acting at a distance, which was unacceptable in the case of special relativity. So now we have many questions that we want to address. And the major open question regarding the standard model is the explanation of why the weak force, that is the force responsible for certain radioactive decays and for the thermonuclear reactions that make the sun shine.
This is one of the four major forces. You have gravity,
that's right.
strong.
These two major forces, the standard model describes weak force and electromagnetism conceptually as a single force. So then the question is that why can we send electromagnetic waves, like for instance radio waves, a long distance, while we can't do the same thing for the weak force? And we think we know the answer to this question, and the answer is the Higgs boson, which is the particle that is actively searched for at the LHC.
The Higgs boson. That's what we've seen some news reports on, that maybe it was detected. Is that correct?
That's right. That's a scientific statement, maybe. So, you know, the particle physics is...
Quantify the maybe. Quantify the maybe for me. How?
That's right. I mean, that's, in every measurement in physics, you have to give the level of accuracy.
Yes.
And there is a statistical properties that we are measuring. We are dealing with quantum mechanics, so we can... in quantum mechanics, you can make a perfect prediction about the probabilities of seeing certain particles, of having particles decay, but not of one single event. So we're always dealing with probabilities and with statistical errors. At the moment, we have, well, the most important result was that the possible region of the Higgs boson has been narrowed down to a very small range of masses, and also within this small range of masses there is some excess, some indication that the Higgs boson is there. Wehowever, the statistical reliability of the result is not high enough to claim a discovery. We'll have to wait.
Okay, so that's the 4-minute explanation of the word maybe. That's what you have there. Okay. Just
I also should say that the LHC is working very well, and we expect that by the summer that maybe will disappear and we'll have a yes or a no.
Okay, Gabby, and we have to start winding down because I want to go to question and answer from the audience. We were speaking earlier. Apparently LIGO is the only experiment that touches all the force regimes of nature. Could you just briefly tell me how that's so?
Well, we are after gravitational effects, but the
And the standard model doesn't include gravity, right? There's no gravity in the standard model of particle physics. Okay, so go. There's just blank stares over there. It means no to them. That's the physicist no. Yeah, it's not there. Okay, sorry.
It's not there.
Can't help you. Go on.
But
no, it's a good. I mean, particles interact with force that vastly exceed that of gravity between the same particles. So it's just kind of irrelevant, right?
Gravity is not irrelevant because it kind of keeps our feet to the ground.
But it's irrelevant to your standard model.
It's irrelevant to particles as far as we can see, but string theorists would disagree. But fortunately, there are none here.
Okay. So tell me, it's gravity, right?
So gravity
That's a force.
is one of the 4 forces. It's the weakest of all forces, and that's why particle physicists think it's irrelevant, because it is irrelevant for most purposes. But it's very strong near very compact objects, like neutron stars and black holes, and that's the gravity we'll be measuring. So we'll be measuring these effects of gravity that have never been seen before, of black holes about to colliding and forming a larger black hole, neutron stars, on which there's a lot of particle physics and standard model being used, colliding and forming a singularity of space-time in a black hole. That's what we are measuring. And that's what I think will give us a clue of not just about gravity, but about nature, all of nature.
So fluency in physics matters here in all these regimes.
Oh, it does,
presumably.
Certainly, yes.
And Laura, just before we go to questions from the audience, let me ask you, what's in the future of the OPERA experiment?
Well, as I said before, our goal is to prove the neutrino oscillations. ∝, so-called ∝ to ∝ neutrino oscillation.
So
this is our
three
goal.
species of neutrinos, and they just switch back and forth among themselves for mysterious reasons.
Okay, not mysterious reasons.
Mysterious
it's
to
quantum
me.
mechanics.
I heard it once described, someone someone throws you a basketball and then you catch a football. That would be a ball-changing species midway.
Footballs are her as soccer.
Soccer ball. Soccer, okay.
Yes, if you like.
Okay, so continue, please.
And so we are planning to complete it. We already detected one event, one so-called tau candidate event. We expect to find a few more before the end of the experiment, something like 5, 6 particles. And the final run will be this year, and so it's about to start again in March. Okay, no, this week. Am I right, John?
Wait, should you be there now?
They see the neutrino beam is starting again from CERN to Gran Sasso, and then we shall have 200 days of run, and then we collect the data, and then we analyze it, and it will be done with this. But at the same time, we will repeat again, and not only OPERA. There are at least 3 experiments at the Gran Sasso beside OPERA and Icarus. There are also LVD and Borexino, which have a new setup to test again, to measure in a really completely independent way, to retest this velocity business.
To do it right, to do it.
Yeah, I mean...
Did it right. Anyway.
So you think that's even necessary because your papers are so right?
No, I think you have to think of Occam's razor in a situation like this.
Occam's razor?
In the sense it tells us you take the most likely scenario, which has been proven in the past. Now, we've never, of course, looked at muon neutrinos.
Well, no, Occam's razor is the simplest explanation.
The simplest explanation here is that the velocity of mu neutrinos is the speed of light. We found that for electron neutrinos. We never found any difference between electron neutrinos and muon neutrinos. That doesn't prove it. But if some experiments start showing that you get the right velocity of light, there's an overwhelming likelihood that they're probably right because they're going according to the established tradition. Whereas OPERA is going against the established tradition and has found an error in their experiment. So not wanting to pile on to OPERA too much here, I'm just saying this has already sort of been the consensus all along. And then we have sort of tested this ourselves. Hopefully other experiments will do the same thing.
Okay, let's assume you're completely right. I would say if you are right, the approach that you have about being right is not necessarily good for physics because I've read about cases in the past where people were just sure you didn't have to test it any further because they'd already done the measurement. And someone with some skepticism kept at it. And they kept trying to refine whatever was the results that they'd gotten before, leading to then a new discovery. Maybe that's the rarer of the cases.
This happens, but it's very rare.
Rare.
Because the collected wisdom of the experimentalist and the theorist are a tremendous piece of information that you have going into an experiment. And actually,
but it can also bias you, can't it?
It's a bias, but it's also how we decide which experiments to work on. An experiment can take a decade or two decades of your life now. So you don't want to go after some wild, crazy idea, where 20 years later you regret you did it.
See, many years ago, Cherenkov invented the idea that if a particle travels faster than light, which particles can do if they're traveling through air or water, that they will radiate light. And Cherenkov effect was observed, and Mr. Cherenkov got his Nobel Prize. And the rather trivial thing that Andy Cohn and I did is to notice that if neutrinos were superluminal, if they travel faster than light, then they too would emit radiation. And that radiation has been looked for, you've looked for it, other people have looked for it. It ain't there. And this unambiguously, I believe, beyond a shadow of a doubt, tells me that this charming young lady is absolutely wrong and her experiment is flawed. Neutrinos travel at the speed of light.
Can I comment a little bit?
Yes, please comment. And then we must go to Q&A.
No, what I want to say that...
in fact, we'll give you the second to last word.
I agree, but the point is not, there is nothing wrong, I think, on being wrong with experiments. We are allowed to be wrong. Because physicists...
David, you lost the crowd.
Physicists, they can be wrong, but physics is not. So at the end, eventually, we will see what is true, what is not. And even what we know now, it will be perhaps an approximation, perhaps in the future will be discovered as a wrong thing. I mean, I'm not defending the Opera result. Actually, I was one which was among the most skeptical inside the collaboration, okay? But we have to, I mean, there is nothing so terrible. The most important thing is to be honest and keep on trying and proving whether or not you are wrong or not.
I have a brief comment.
No. Okay. So no, sorry.
I'll do it anyway. It's one thing to be wrong. I agree, we all have the right to be wrong. I've been wrong myself. But it's another thing to have a big press conference, a big press release from a huge laboratory, which we all depend on, CERN.
This is not our fault.
Well, it may not be your fault, but it's what happened, okay? So being wrong is our right. But having this sort of information go all around the world, so a lot of young people get the impression that neutrinos travel faster than light, it might be very exciting, but it's probably not true. So.
You say that as though to like mess up young people forever. Like, well, young people heard this newscast.
I'm sorry. I don't think it's good to give young people, I teach them all the time, wrong information. Now, I don't say they'll never forget it or they'll have a heart attack or something, but as much as possible, the veracity of science is based on, as much as possible, getting things right.
Yeah.
That's all I'm saying. A press release is hardly just a little bit wrong. It's all over the world, instantly. The day it came in, my student sent me a message immediately. You know the speed of light for neutrinos was greater than the speed of light. I mean, everybody was saying this. You know, a lot of us never believed it all. I mean, in no disrespect. Shelley didn't, he said it already. So I agree you can be wrong, but I don't think it's good to advertise it so heavily.
Except that your best evidence that it's wrong only came out in a paper 5 days ago.
Now, we had a previous paper, which I told you about 6 months ago.
Just checking.
It's true. It's true.
What's the future of GPS? We're gonna. I wanted to drive my car. I just want to like read in the front seat.
Yeah.
So can you do that? And how come we don't have flying cars? I'm going to blame you for all of this.
Right.
They promised flying cars in the 1960s. They're still not here.
They have them in Italy.
Oh, I got to stop it there. But thank the panel for this. You can come on up for questions. We have 2 microphones up front. We'll take Q&A for about 15 minutes. By the way, the entire panel and I, after this, will retire to the Hall of Northwest Coast Indians. That's where all the totem poles are. And you can bring your program, have them sign it, ask follow-up questions. There might even be a few books that they've written for you to buy. Okay, so, oh, by the way, we have 1,700 people streaming this live. And hello to all of them. And we also have an overflow room. And so let's take a first question here. Try to direct it to only one panelist. Otherwise, it takes forever to say, can I have all 6 of you comment on my question? Just keep it tight. Go.
Okay. All right. For the gentleman, I don't remember the name, but
John.
From Italy, John.
We're on first name basis. We're at a bar, remember?
Very
yes.
Good. I guess I'm less interested in maybe the results that came out from opera and more interested in the physics community's reaction to it. And by that I mean, you said you were all curious, but is there some sort of deep-seated insecurity that theoretical physicists have, where when something like this comes out, they say, aha, that may be the missing piece of the puzzle that'll allow everything to click? Or is this just an anomalous thing that was 60, I don't remember the measurement you used, but
got there 60 feet faster
60 feet faster, and you just say, wow, that's really big, we're going to go analyze it.
Excellent question. What do you got, John?
So, you know, when there is some interesting announcement, of course, we have to look at it, we have to scrutinize it, and we have to see if it makes sense. That is, as I was saying before, that's our job. I don't think we should be blamed for that. But I totally agree on what David said before. The particle physics has a tradition of rigor, of scientific integrity, and this should be maintained. And, in the past, physics was just particle physics was a business for particle physicists. They were getting great results, they were enjoying, but most of the people were ignoring. Most people outside were ignoring what particle physicists were doing. Now, there is a lot of media attention, and as David said, we have to be very careful of what kind of message we are giving. And in the case, the opera case, I don't think it was a mistake either of the experimentalist of going public with the result or of theorists to try to make sense of this result, but rather the way it was dealt in the way CERN and the opera experiment communicated with the outside world.
John, I'm going to follow up on that. John, of the theorists you knew, how many said, it can't be true, I'm not going to work on the problem, go back and fix it? And how many said, that is true, I have a new theory to account for it?
Well, of course, no. The first reaction is, wow, this is too great to be true, right? But in order to answer, you cannot just reply with your first feeling. You have to study, you have to look at it. And Shelley was so nice to mention my paper, but I would say that really the paper that changed the opinion of the community was his paper. His paper gave a very strong, very clear, very simple argument of why it was the opera result was inexplicable. And at that point, really people changed their opinion. So people, even theorists, don't form the opinion just on their first impression, but they want to get some scientific understanding. And I think after Shelley's paper, the situation was very clear.
Okay. Right here, sir.
Thank you.
Yeah, I was actually up at the APS meeting in Boston about
American Physical Society?
Yep.
Yes. Mm-hmm.
And
has nothing to do with your body, it's physics. In fact, they had it, I got a phone call from their PR people. They said, we have an identity problem because people think we're about physicians. And so there's American Physical Society.
Yeah.
It's really American Physics Society, but yes, go on.
They actually had tucked away way off on the side a talk where we were talking about some of the results of the opera experiment and so forth. And the thing that was pointed out by the gentleman that I remember the most, and I would like her take on this, is that this kind of science controversy is actually good. It's not a bad thing to have publicized wrong experiments, and even if it's a, quote, simple mistake or an experimental thing, because it does not treat science as a black box, and therefore the public can understand it. And so it's not necessarily, here's a result, and don't ask how we got it, and you're not going to understand.
I think that was Laura's concluding point.
Right.
She agrees strongly with that, and both of those points disagree with David, in the sense that you go public with it if you think it's true, whether or not it's consistent with the experiments or the theoretical underpinnings that you've put forth. It's just, if you think it's true, you go to press with it. So you're agreeing.
With her point, and I wanted to know the broader panel, unfortunately, point of view on that too. Is science controversy good or bad in general?
Shelley, let's go to you. You've been around the block on this. Science controversy, would you say it's good or bad, or?
Well, what is good or bad?
If hanging your dirty laundry out, right here, check it out, right there, dirty laundry. The scientists doing that. And the dirty laundry would then take place via a press conference, and then you see scientists fighting.
Yeah,
it's kind of what this whole panel is all about, the Asimov concept is all about. And we fill the house every time. So I have to say yes to that, but I just want to get a second opinion. And if it differs, it will be wrong, so go on. Because we have empirical evidence.
We guys who do what we call fundamental physics, particle physics, we have a problem. And the problem is called the Standard Model. And the trouble is that the damn thing works too well. And since the old days when Carlo Rubbia was in charge of CERN, and Carlo Rubbia once gave a talk at Harvard arguing that he had not only proven the standard theory right, but he had also proven it wrong. And that was shown to be not true. And his punishment was to be the director of CERN for some 5 years or so. And his CERN in those 5 years did nothing but confirm, and reconfirm the Standard Model. It was truly a Sisyphean punishment.
He also started the LHC.
But he started the LHC, and our hopes are that the LHC will discover something beyond the Standard Model. And I was so happy when I first heard of the superluminal neutrinos, because boy, that is beyond the Standard Model.
I got a question from the Twitterverse.
But it doesn't work. It's wrong.
A question from the Twitterverse. So the Twitterverse does exist. I have evidence. No matter what you say about it. I'm sorry, I can't read the Twitter handle. Mastrician. Are there currently unmeasured domains where we can imagine faster than light particles? Possibly highly warped space-time?
I can imagine micro-unicorns, but...
That would be a no? Okay. Next question here.
Are there any insights from the neutrinos on dark energy, string theory, and black holes? Is there any connection from your research?
So you're trying to explain all the other unknowns with what we might discover with neutrinos. David, why don't you take that?
I'm sorry, I didn't quite hear the question.
He's taking dark energy, dark matter. He's got these other unknowns.
Okay.
Might neutrinos help us there?
Neutrinos have a small mass that is not nearly large enough, let's say, to make the dark matter of the universe. And they cannot in any way make the dark energy. That's been proven. So these are other phenomena, and we have some idea of what the other two, like dark matter, is probably some new kind of particle. Dark energy may be what Einstein invented in 1917. So probably there's no connection as far as I know.
What about string theory?
I don't know anything about string theory.
We've established that string theory is off limits today. We've already established that. Another question from the Twitterverse. This is from our development department, apparently. Will Trammell, 13 years old. Oh, sorry, from our live stream. Will Trammell, 13 years old. Is this past your bedtime, Will? Don't know. Past my bedtime. Neutrinos can pass through almost anything, but light cannot. So could neutrinos be faster than light because of this lack of friction? And could we measure this friction rather than the speed of the particles? So in other words, neutrinos got to Italy, but light didn't. So clearly, that beam of neutrinos beat any light beam you would have turned on with your flashlight. So is the fact that neutrinos can penetrate solid matter any kind of indication of anything?
No.
Okay, fine. Okay. What you got here? I like these quick answers, are great. What do you got?
I'd like to actually answer a question that I believe Sheldon and David posed to us, which is what is the effect of experiments like the opera experiment to young people, and what message is that sending? And from a moderately young person, I can tell you that the message that it tends to send is it invigorates us and inspires us to investigate and see that maybe the plausibility of the impossible can exist.
Yeah, that was for me, I guess. I wish that was true.
He wasn't talking to you. He was like, he was just...
Let me tell you something.
What's that?
At UCLA, most of my graduate students are Chinese. This is because very few Americans...
And that's relevant why? Okay.
And by the way, the Chinese are paying some of these people to come to our university, which is a very clever thing for them to do. Probably other places also. So I don't think when people find out that something they were told turns out to be wrong, my own gut feeling is it just makes them wonder whether these people can get their act together or not. Now, maybe for a while they'll be stimulated. The evidence right now is not nearly enough Americans are going into science.
Yes,
I don't think
but
we want
that's
more.
my exact point. I'm sorry to interrupt you, but isn't that my exact point? Sometimes it's not just the science of proving, but the science of disproving.
What you say?
It's just as educational.
You're saying that there aren't enough Americans in our science programs today
Yes.
because of the opera result?
No.
I'm just trying to get the cause and effect here.
They don't even know anything about it.
I have to get to my question.
I'm just saying.
Oh, you have a question? Sorry. Let's get to his question.
So anyway,
Go.
the point is there are tangible experiments going on, opera, for example. But can you then, instead of saying, okay, this is not possible because we have too much that's in our black box of comfort that does work, so I'm going to disprove it. Why can't people sit down, such a scientist as yourself, as even if it dissembles the structure of physics, we know that physics violates its own rules all the time, as we've seen from history, right? So can we, by the equations, not just by the tangible experiments, but by the paper experiments, go back to rudimentary tactics and try to see what potential effects it would have on our box of comfort in science?
If it were true.
If it were true.
Let Shelley answer that.
I don't understand the question.
No, I think what he's saying is, you have this weird, I think I understand you. You have these weird results. You don't know how to interpret them. Assume they're true and calculate the consequences.
Correct.
Well, that's exactly what I did. And the
Okay, right.
that's what we do. That's our
Okay,
game.
no, so he did say, he said, if that were true, you should have these other experimental results that are not seen.
Can I add
Laura,
something
yes.
to this? There are a lot of anomalies still in the neutrino field. All the results with neutrino oscillations, they do not fit all together in the same good box.
Black box of comfort was the phrase.
And so you can take them as anomalies or errors, or you can take them as an indication, hints of something else. And then if you take them for true, then you may want to investigate more. For example, there is a proposal to do this for as far as neutrino are concerned. We would mean, for example, the existence of another type of neutrino, so-called sterile neutrinos, which are very exotic. I don't know if our guests here like them or not. Many people do not.
I bet he doesn't like them, is my bet.
Yes, David doesn't like them. And
say one-
anyhow, this is the way you proceed. I mean, and then you test, and then maybe it's all a mistake, or maybe you find a new particle, and again you go to Stockholm.
Stockholm. For the Nobel Prize. That's code for Nobel Prize in physics.
Thank you.
Thank you for that great question. Yes, and I want to, we'll take maybe 5 more minutes of questions, so maybe we make the question efficient and the answer short will be good. Go, sir.
Well, I came up for other reasons, but they've already been asked. I think.
Okay, fine. So
the neutrino experiment was exciting because we got to watch you guys go through finding the problems of the experiment. Everybody I know knows about the neutrino experiment, and they're not scientists. It's been very engaging. Watching you not fail, but discover the problems is really interesting. I won't belabor it because
that's an excellent point. Thank you for that.
It's been great. Thank you.
It's been great.
Thank all of you. But this is actually for David. The United States had the collider on plan years ago. Budgets got canceled.
Yes,
now
we
we're
had
over
the-
at CERN.
I
Any
can answer
plans
quickly.
coming up?
We had the superconducting supercollider,
Right.
which actually was, kind of believe it or not, approved by Ronald Reagan, which in some way we don't fully understand why we do better in the Republicans and Democrats. Maybe I shouldn't be too political, but...
And science funding, that's a
Then
fact.
Bill Clinton canceled it, so you can figure it out. Anyway, whatever the reason is, we lost a tremendously wonderful scientific resource in this country, which might have brought a lot of more American scientists into the field. And then, of course, now we have the wonderful LHC, which was started by my friend Carlo Rubbia, I point out, who was the Director General of CERN. And that is still, a lot of Americans are working there, so it's still helping generate more interest and more excitement. But we have sort of lost our momentum in this country, a little bit the way we have in NASA, on science. And I think young people are starting to notice that. I've noticed a number of young people have told me they themselves were kind of disappointed when they heard the superconducting supercollider was canceled. So they're looking for their future. So I think we have to really worry in this country about the future of our fields.
I bet if you had called it the Super Duper Collider, it would have been funded.
It would have been funded.
You had an absence of adjectives there. You could have called me up. I would have helped you out. Yes?
This question is for Laura. I was wondering if you could tell us briefly the logistics of how the opera thing was set up. Because I'm a physician, and very often if we find a result which is out of what is expected, the first thing we do is just repeat it before we go and act upon it. And it sounds like, I mean, from our point of view as non-physicists, this came out and it was so shocking thing this was found, and you're trying to explain how could something so unexpected happen. Was this a kind of experiment which, when you got a result, which, I mean, maybe for you it was not unexpected, but I mean, it sounds like it's an unexpected result, that this could have been repeated in a quick time frame and come up, say, with the same result twice, then you start to think, well, maybe there's really something happening. If you
Well, that's exactly what happened. This experiment was done more than once, isn't that correct?
Sorry,
Was the experiment done more than once?
Yes, I mean, we started in 2009 and kept going on until 2011. So we analyzed more than 16,000 events. Right. Neutrinos, 16,000 neutrino events detected from CERN to Gran Sasso. It was not just one or two neutrinos.
Right. In fact, the anatomy of this is, in all of science, is if you get a weird result, you do it again, just like you said, and then you do it again, and then do it again, then you get someone else to do it with a different apparatus.
Right.
And that's
where it came across from the announcements that it was done in one lab, and then other labs were then going to repeat it with their equipment and to see if the same thing came out.
That's the natural
but
sort of sequence.
But it didn't come out that it was really a multiple events at that time.
The point here is, it has already been mentioned, the difference with the past is that it's not unusual that something which is, that you find it is correct, and then you have to say, no, I was wrong. The point was that it was known to everybody in the world. This was the main difference. I mean, there are plenty of examples in this sense, of this type, in which many experiments then were corrected, eventually corrected, that eventually were wrong. But I mean, nobody knows, no? But in this case, everybody knows. But I mean, this is the new society, no?
I think the press distorts things sometimes.
You think the press distorts things?
Well, there is good and bad to that. I mean, I don't know.
We're running really short on time. I wanted to end at 9:15. Maybe just two more questions. I'm sorry if I only take two. But if you come to the table in the back, I'm sure they'll be happy to chat with you. It just won't end up as a publicly announced question. You're the last two here. Yes, go.
Okay. Concerning the speed of light, which is the thing everyone's measuring it against, that no one has asked a question about, which is this. When Einstein was writing all this, nobody knew about dark matter or dark energy. We know that when light enters the atmosphere, it travels more slowly than in interplanetary space, and when it goes from the atmosphere to, say, water, it travels slower still. We now know that interplanetary space, and indeed interstellar space, has a lot more stuff in it than we used to think, and that it is less of a pure vacuum. Is there any room there that light actually moves a little faster than we thought? And that this isn't so much that they're moving faster than the speed of light, but that the speed of light in a real vacuum is actually faster than we thought it was.
Yeah. Shelley, so if I paraphrase the question, if I may.
Please.
Okay. We have this 10-digit precision definition of the speed of light. And that's the speed of light in a vacuum. But there is no vacuum. We've never actually created a vacuum. We've tried to approximate a perfect vacuum, but there's always some particles left over in the space in which we're measuring the speed of light. You go out to interplanetary space, there's stuff there. Intergalactic space, there's stuff. Light is never traveling through a vacuum. Is there some speed that it actually could attain that's higher than anything we've measured it to be if, in fact, we could send it through a perfect vacuum?
Yes, the answer is yes. It's easy the things that are out there in space are mostly photons. The universe is not at absolute zero. It's at 3 degrees Celsius.
Kelvin.
Lots of photons.
Kelvin. 3 degrees Kelvin.
2.73.
2.7. That
You said Celsius. I'm just saying,
Kelvin.
it's the wrong temperature scale.
2.7.
Mr. Nobel laureate from the Bronx High School of Science.
3 degrees Kelvin.
that.
3 degrees Celsius? That's
Only
like
wrong
a
by 300.
chilly day outside. Okay.
Anyway.
Anyway, all right.
No, here it is.
I have to gloat in this moment, please.
Did you say Celsius?
It's not at absolute zero.
Right.
And therefore, light travels more slowly than it would travel in a vacuum. And we can calculate that difference, and it's in the 47th decimal place.
Gotcha. Okay. Good answer to that. The very last question, so it better be an awesome question.
That's for Laura. Question. I'm a scientist, engineer. You made something that was so dramatic, it shook up the world. Shook me up, shook up those two guys, definitely. But what I don't understand...
And Elvis Presley's all shook up, you know.
What I don't understand is what happens at opera, the management there. They had to realize that this thing was so dramatic, so unbelievable. That's why everybody's here. You know, it just happened recently that you ran another test that said you're wrong. And then within just a couple of months, opera comes out and says, we're wrong. Wouldn't you, something bothers me that you should have gone back and checked and checked and checked.
For those 2 months?
Yes.
Rather than even announce
That's my question. What happened within opera? Who makes that decision to go out?
So that's the management of science at that level, of the publicity and the publication.
Yeah, but
excellent question. Excellent question. If they found the answer within 2 months,
yes,
then why not wait another 2 months and do all the same analysis
Yes.
and not have published the result at all?
Can I answer like this? No comment.
Should we end on a no comment?
No comment.
Let me. Last point here. So, ladies and gentlemen, so does the future of physics, John, is the future of physics bright? Is there new discovery just beyond your reach that'll transform all of our understanding? Or is it all about just adding a few decimal places of precision?
During history, many times people have repeated that physics is over because now we know everything, right? And at the end of the 19th century, people thought that's it. We know everything because we have perfect theory of thermodynamics, of optics, of mechanics, and so on. And then just in a decade, relativity came, quantum mechanics came, and the whole world was revolutionized. So I think that will never be an end of science. I don't think we are at the end of science. But there are moments in the history of science where we are at the end of certain paradigms. Certain ways of thinking are finished and we have to open new ones. I think now we had the age of the Standard Model, which was an extremely successful age, where we have a beautiful understanding of the particle world, and this understanding can be expanded to the complexity of the world. Now with the LHC, we are at a turning point, and we will see. And depending on the result, we could be at the verge of a new revolution. I think we'll have to wait for the results in order to...
Okay, he just wants to raise the results. Are we also waiting for the birth of another Einstein?
No, I think the fundamental question in dark energy is whether we can calculate the level of this or not. And that's more of a theoretical question than an experimental question. The other question is, what is dark matter? There are a very large number of very interesting questions left. They may not just be done in the traditional way with colliders and accelerators, but they'll be done in other ways.
Are you smart enough to figure out those answers, or are we waiting for the birth of another Einstein?
We need another Einstein to calculate the dark energy.
Okay. Shelley.
What we need are surprising, unanticipated discoveries. When I first heard of the opera result, I was delighted because it is so inexplicable, so wonderful.
The truth comes out.
Unfortunately, it went away. We need surprises. We are the only science that depends on results that contradict our own theory. We want to be contradicted.
Where, in fact, fame derives from contradictions of established theory.
Absolutely.
Unlike so many other professions in our world. You're just happy with your GPS.
Yeah,
so,
no, hold on.
Okay.
Your
GPS is working.
Well, I just wanted to point out one thing, that even if physics is going slower, there's still a tremendous amount of technical work out there for engineering actually to catch up with the science. There's all kinds of things on the horizon.
You just look at these machines that they're building.
Quantum computing. There's Fermi Lab put out a press release that they actually could communicate by sending neutrinos. How exciting is that to have a communication system that can actually go through rock, aside from the fact that you need a 27-kilometer transmitter to do it? Maybe you can make that a little smaller and we'll get more excited.
I'd rather just send a text, that's much easier than sending a neutrino. That, I don't know.
But I think there is a great deal of work to be done in bringing some of these very newfangled things that I've been learning about before this thing into to things that you find in your house, more so.
Laura, is physics waiting for a new Einstein, or is everyone alive smart enough today to solve all the problems?
Well, no. No, I was thinking another thing. Can I conclude with another thing?
Sure. Okay.
Because now I was wondering, which is the main important point for me as far as physics is concerned, and I would like to be able, maybe my daughter, to answer to the question: how is it possible that we are tonight here? By this I mean what made possible at the beginning that the asymmetry between matter and antimatter.
One of the most profound questions that exists in all of physics.
Yeah.
How there is matter.
And this is something which is thrilling to me. So
you lose sleep over this?
Sorry?
You lose sleep over this?
Well, I lose sleep because of the jet lag.
Okay, so there are other questions that are, I agree. The asymmetry of matter and antimatter in the universe is profound. Had it been symmetric, all of our matter particles would have annihilated with their antimatter counterparts, and we'd live in a universe of just photons. At some point, that symmetry was broken, putting 1 out of every 100 million of these interactions, leaving a lone matter particle without an antimatter particle to annihilate with. And we are the manifest of that result. I agree. Gabby, are you the next Einstein?
No. I think there are many, many Einsteins out there.
I think they're like investment bankers or something. We got to get them out of that field.
We do.
Yes. The whole lost generation that are like billionaires now that could have just solved physics.
But I think this is a very exciting time, especially for experimental physics, because we have such high precision detectors. We have such exquisite precision on space missions, looking at the universe, on particle detectors, the colliders, our detectors looking at the birth of black holes.
We're data rich.
We are data rich. Very data
and
rich.
Theory
we
poor.
just need people to look at it.
Data rich and theory poor. I'd like to end on a quote from Isaac Asimov himself, where he said, I'm paraphrasing, he said, the most important revelation a scientist can have is not eureka. No. It's in reaction to an experiment where the scientist says, that's funny. That's how that begins. Great discoveries in physics happen because just some one little result doesn't match something else that you expected. And you say, that's odd, that's peculiar. Let me just look at that a little more closely. Let me design an experiment just for that. Let me see if I have an understanding of it. Maybe I need a new theory, maybe I need a new experiment. And such is the life of this panel, and I want to publicly, with all of us, join me in thanking them for coming, and thank John Carlo. I think physics looks good if they're represented by who we have here on stage. Thank you all for coming. We're calling it a night. We'll see you next year.